Now, these examples with the FCC comments leave us with a lot of really big questions about how we can use computer software to analyze large collections of text. And the first of which is, if we have different text documents, how are we going to measure the similarity of those documents in the ways of the previous example? So looking out for text that might be off by one sentence, that might be the same but have sentences rearranged, or might have a lot of very similar structure and a lot of very similar words within them. Second might be, can we tell the difference between things that were written by people and things that were written by bots? And we have to be a little bit careful when we perform this kind of analysis in thinking about both sides of this, because some of the things that bots might do are meant to mimic human behavior. For example, John Oliver covered this FCC story and encouraged many of his subscribers to go out there and leave comments to the FCC. Naturally, a lot of those comments are going to use the verbiage that he might have used on his show, and that's a natural occurrence. Those are still people, and they're still part of perhaps a letter writing campaign, if you will. There might be a lot of similarity and overlap between those collaborative efforts. However, there should still be something human about them, and we want to be able to distinguish grassroots letter writing campaigns from bots that are mass producing the same type of comment. And of course, we may just be invested in this story now, and we might want to know the end result for the FCC comments and net neutrality, both what happened with them and what the analysis really showed the comments were saying. So let's get started on the things that I'm more skilled to talk about, which would be the mathematical and computer science analysis behind this. Here are some old answers, shall we say, things that might come to your mind immediately for ways that we could analyze this problem. What we're going to do is take every single text document and totally strip it of its order. We're going to take the words that occur, we're going to count them, and we're going to store them in a big long list of words. We're going to take every word that appears in every comment and use that as our dictionary, and then we will run through a document and count the number of times that that word occurs in the document, again, regardless of the order in which it occurs. So I've started out with our very small comments here, and I've made those lists of words. Maybe if these were our first few documents in the corpus, we would have don't kill net neutrality as words that we need, and we would go on and we would have the flow of, and you can see that words like don't kill net neutrality only occur once in this document, but words like the and of occur a little bit more frequently, and so we'll make those numbers 2 for the number of occurrences of those words. If we were going through and doing the same thing for comment D, it doesn't have that first sentence, don't kill net neutrality. Those words don't appear in this comment at all, so we put zeros there, but we still have those words like the flow of that are occurring with those frequencies, and so we'll keep track of them. In this sense, we will catch examples like the second example that we showed, where the reviews and the comments were absolutely identical, but the order of the sentences has been changed. They will have the exact same words appearing with the exact same counts. And since we're not keeping track of order here, those two different reviews will have identical lists of words. And this is sometimes called the bag of words model that we studied when we studied logistic regression. And once we have taken a text document and translated it into these word counts with our bag of words model, we can use our age-old distance measure that we've been using since we computed the distances between points in, let's say, middle or high school, which is the Euclidean distance. So just in case you need to be reminded of that, or you'd like to see it with our example that we've been using, we have these two different lists of words, and we're thinking of them as appearing in the same order. What we're going to do is we're going to take the difference component by component all the way down and come up with a brand new list of differences. And we're going to do just a subtraction right here, top minus bottom, and put that value into this list right here. And these are going to be the differences between the two texts that we're reviewing. Now, it just so happens with this example that everything here is positive, but if I would have taken the difference in a different order, if I'd have swapped these two and done the subtraction, these would all be negative ones right here. And so we don't want to just add up the collective differences, since that pays attention to the order in which you took the difference. So in order to solve that problem, as we've seen before, we don't want to put absolute values in here. Those get computationally messy. So instead, we'll trade absolute values for squares. So we'll square, component-wise, each one of those differences to remove any minus signs. In a sense, I've selected a poor example because all the way down we have zeros here because these two documents were identical up to that first phrase, and I had to square all of these ones. They just stayed ones, but if this were something like a 2 here, we would have a 4 here. And now that I've gotten rid of any potential minus signs, I'm going to add up all of the numbers in this last list, and then I'm going to take their square root to kind of compensate for the fact that I squared right here. And so all in all, I would get an answer of the difference between these two vectors is the square root of 4, which is 2. And that's pretty small, especially if you start thinking about text documents that have lots and lots of entries and go on and on. So we could say that absolutely identical documents that have their sentences moved around will have distance 0 from one another, and we would consider them the same. If we then find different reviews that have a very small Euclidean distance between them, we think that they're incredibly similar, and we could set this threshold for saying if you have a Euclidean distance less than a certain amount, we're going to consider these documents to be the same, and if you have a Euclidean distance of greater than that same threshold, we're going to consider these documents to be unique. And that is a good initial model to use. It's accurate, it's familiar, and it's going to catch some of the problems that we've seen. However, that method is going to have a couple of problems which we'll want to try to resolve that we'll focus on in the next video.